probably have an idea by now of what a machine learning pipeline looks like, but let's go over it formally here. To begin, you'll want to collect data. For most deep learning applications, you'll need lots and lots of data. This data can be stored in any number of formats: WAV files for audio, comma-separated value files, arrays in computer memory, and so on. For supervised learning, which is most of what we'll be covering in this course, each data sample will have an associated label that will assist the training process. Then we perform feature extraction. In some cases, there will be a pre-processing step, such as filtering the data or cleaning the data to make sure we have a representative set. Features can be any number of items that are calculated from the data. We looked at calculating the root mean square of each axis in each sample, as well as gathering information about the power spectral density as our features. These features are then saved in a separate set of files or memory arrays. Note that the labels are associated with the features as well. If the first raw data sample has label 1, then the features calculated from that data sample will also have the same label. These features and associated labels are then used to train our machine learning model. The training process, known as backpropagation, updates the parameters inside the model to help make it more likely to predict the label of each feature set. This can take hundreds or thousands of iterations to have the model make fairly accurate predictions, assuming we've done a good job of extracting features that represent the original data well enough. Let's go over the concept of parameters versus hyperparameters here. You'll hear these terms often in machine learning, so it's important to understand the difference. A parameter, when it comes to machine learning, refers to any of the variables and coefficients inside the actual mathematical model itself. These are the numbers used to make predictions when fed features as inputs, and they are almost always determined automatically during the training process. Rarely do we set parameters manually, as our training algorithms are configured to figure out which are the optimal parameter values to use for the model to make predictions. A hyperparameter is any configuration that is outside of the model and whose value cannot be estimated or tuned by the data. These are the configuration values that we must set manually, such as the size and shape of the model, the learning rate and number of training steps to take, which features to use, and the methods and calculations to pre-process the data. A good rule to remember is that if you have to set a value manually, then it's probably a model hyperparameter. We can create a program to automatically try different hyperparameters to determine which works best for the model, but since they are still outside of the model and training algorithm, they are still considered hyperparameters. Once we have a model that performs as we hope on the training and test data sets, we can deploy it to our microcontroller. The model itself is essentially a collection of parameters, which are just numbers, and some mathematical operations. As a result, the model can be stored in memory on a computer or microcontroller as a collection of functions to be called by our program. The easiest way to think about a model in this instance is like a program function. We provide it with a number of features as inputs, and it gives us its prediction as the return value. In the case of supervised learning, it will tell us which class it thinks the input features belong to. The process of using a model to make predictions on unseen data in your target system is known as inference. The idea is that the model has learned everything it needs to know to be useful and can then start inferring meaning from new data. Because the model is expecting features as inputs, it means that we need to do the exact same feature extraction process we used during the training step. And similarly, any pre-processing we performed will also need to be done here too. Finally, to get that raw data in real time, we'll have to collect the data. In the case of embedded machine learning, this data collection process likely means reading raw inputs from sensors. Rather than saving the data and features as separate files or arrays to be used multiple times in a training process, we often set up the pipeline to be one continuous flow of data and features that get used in real time. Note that while we are doing data collection manually, many of these steps can be automated. For example, Edge Impulse has an ingestion API that lets you send data to your project programmatically. This can help you automate the whole process, including training. While we won't cover the ingestion API in this course, know that it is an option for your projects and products when you're ready to scale and automate the collection and training steps. If you've worked on large-scale, enterprise-level software, you might be familiar with the concept of DevOps. This is a collection of practices that combines software developer and IT operations to shorten the development lifecycle and provide customers with continuous delivery of high-quality systems and support. It came from the Agile methodology and is popular in the software world. As machine learning grows in popularity, we're seeing a rise in the need for people who can integrate machine learning into large enterprise-level software development efforts and combine that with the necessary operational support. This is giving rise to machine learning operations, or MLOps. Similar to DevOps, it brings data scientists into the fold to ensure that the right kind of data is being gathered, removing biases in that data, and helping the development team construct useful models to meet the needs of businesses and customers. We will likely see the need for more of this integration in the future, even for embedded machine learning. In fact, new data may be collected in the field that prompts the data scientists and developers to update their model and redeploy it to all the devices already in the field. This creates a similar problem to what we've seen with the Internet of Things. How do you maintain and update firmware running on thousands of devices in the field? While this type of large-scale deployment and maintenance is outside the scope of this course, I urge you to keep it in mind if you're planning to build machine learning into your next embedded product. Additionally, if you're looking to do more project management or software development, it can be useful to add DevOps and MLOps practices to your toolset.